Okay, so I want to give you an overview to help you understand Chapter 6 more. And it starts back at the beginning with Chapter 1. By the way, there's going to be a bunch of shifting through PowerPoint slides and other images. So I'm not really worried about how pretty this layout of the video is. So if you don't mind, ignore that. In Chapter 1, we got to know what data was, data collection, designs of experiments, and things like that. So there wasn't a whole lot I want to review that. And then in Chapter 2, we started to show how to summarize that data in several ways. One of the most important ones at the time was the frequency distribution. And then from frequency distributions, and we have different types, by the way, we could create histograms. And so, of course, we had different types of histograms, and then we could create other graphs. And that all helped us to summarize data. So let me give you just a brief reminder. So suppose you had a big pile of data for the ages of Best Actress Awards winners and Best Actor Award winners for the Academy Awards. It would be hard to tell if there was anything different between the distributions of data or between the data unless you looked at the distribution. So what we would do is we'd create some sort of a frequency distribution, and here's an example of the Best Actress one. And then you start to be able to tell that there's some sort of a characteristic that is in the female, the actress award winners, versus the characteristic that is there that's not in the best actors. You really need to do both of the distributions, but here is the female one, and without doing the male one, you can take my word for it that you'll notice that there are a lot more younger aged winners. You'll see the frequency is much higher in the younger age than there is in the older age. And that more clearly seen when you start to take these frequency distributions and make histograms. Before I remind you what the histogram looked like, though, let me show you the other types of frequency distributions. There were the relative frequency distributions, when we would take each corresponding class and divide it by the sum of all the frequencies. So the frequency for a class divided by the sum of the total frequencies. So here is that exact same distribution of actresses. And you can see here's those younger aged, actually the top two between ages 21 and 40 where 58 of the Best Actress winners were in the younger age group. But what is that as a percentage is the real question. So if you turn it into the relative frequency distribution, you get the scores instead of raw frequency, you get the percentage value. So 28 divided by the 76 total frequency or total actresses that were accumulated for those years turns out to be 37%. And 30 out of 76 turns out to be 39%. And then you can see how clearly this bias, this younger age bias, was for the actresses, because that's, what do we have there? 76%, an overwhelming majority, more than 3/4 majority. Then we have the cumulative frequency distribution, which was another way to look at the data as it progressed over the total number of intervals that we have separated. And so what that did was we'd take the values for the frequencies and we'd add into and accumulate the size of the frequency as we developed the table, as we distributed the data. And so the last value would say, the last interval would be the less than 81, which was all of our data, and there were 76 actresses that were aged less than 81. So those are the different frequency distributions: the regular frequency distribution, the relative, and the cumulative. Now that helped us to take, let me go all the way back, a big pile of data, just numbers, and start to put them into a summarized organization of the shape and the distribution. And we're going to see it better when we go to the histograms. Keep in mind, by the way, though, the drawback to this form of summarizing was that we lost information. We now know that there were 2 people that were in the age 61 to 70 bracket, but we don't know if there was ever anyone that was actually age 69, for example. In fact, look at my distribution over here, and there was someone that was 61, and Can you see the second person that would have been in that interval? Here's the 63-year-old. So clearly there never was a 69-year-old, but we wouldn't have known that from this because we've lost details. In other words, it doesn't preserve the data. It summarizes the data and helps us to look at some of the characteristics of the distribution, but doesn't tell us everything that was there. Now, if you wanted to remember one of those, let me go further to chapter 2. You may remember this one called the dot plot. This one does show us the distribution and helps us to know if there was ever someone who was age 69, for example. And it depends on how accurate you make the scale down here, but according to the scale here, we can see that there was no one in age 60 that was age 69. So this one is a way to see the distribution and summarize the data without over summarizing it. It preserves the data. Speaking of another one was the stem plot. Do you remember that? We would put the tens values as the stems, and then the leaves would be the ones values, the units place. And so we could come down here and see that we had a 60-year-old, a 61-year-old, and a 63-year-old, but never a 69-year-old. So anyway, I'm going to digress if I spend too much time on the other graphs, because I want to focus on how we were summarizing the data, changing it from just a pile of numbers to a distribution, and then we would start to graph that as a histogram. So here's a histogram of the relative frequency for that exact same set of data. And we're starting to see a distribution here, and we're starting to see the younger age actresses getting more awards than the older ones. And there might be a reason for that, and then we start to investigate that. What's significant to us with this is that it's not a normal distribution, and that's what we're going to be talking about in chapter 6. So you'll notice that it's got this right skew, or this what we call positive skew, because it's like you're pulling on the positive side of the number line over here, or you're pulling to the right, for example. And I don't really have the drawing here. Let me see if I can draw this out. Hold on. Okay, so I'm going to try to make a frequency polygon. Ooh. It's not going to happen very well. So I'm not going to worry too much about it. I'll start over at least. But so I'm going to the midpoints here, and I'm connecting the heights of the frequencies above the midpoints. And anyway, you can see that this is not normal or bell-shaped. So let's see what that bell-shaped mean. That phrase means. Switch back over here. So the different types of distributions we had were one that was symmetric, and symmetric also applies to something like this. It's symmetric, vertically symmetric, but this symmetric started low, went high, and ended low. So this one is one that we called a bell distribution. Now here's the type of skew. Actually, it looks very similar to the one we just looked at, that had a right skew. Okay, or we also call positive skew. Think about pulling it towards the positive side of the number line. Numbers get bigger. Here's a skew that's the other way. It has left skew. Okay, and here's a bimodal where you could argue that that's symmetric because it's got high up here and high over here, and if you folded this down a vertical line, it would kind of match. But this is bimodal, so it's also not bell-shaped. All right, so this is the one that we hope to have most for the predictive nature that it gives to our data. But sometimes you're not dealing with that, and you're dealing with something like this or this. So you take what you get, but we just need to start to understand them all. All right. Then we went to chapter 3, and we started focusing on some more of the quantitative characteristics and defined for you the measures of center, the measures of variation, the measures of relative standing, and showed you another type of plot that put the 5-number summary together. So just a quick reminder of those. Measures of center, we have mean, median, mode, and they're all trying to measure, we have mid-range. They're all trying to measure what the middle of the data is, but they all do it differently, and they have their pluses and minuses but the fact that they have pluses and minuses is what helps us bring them all together to try to focus on what is normal and what is not normal. When they all line up, we'll have a normal distribution. When they don't, we have some other types. And so knowing which one is more sensitive to outliers, which is the mean, helps us to follow which way the skew is going to go. So let me see if I can remind you about some of those characteristics. So if mean, mean, and mode line up, we've got a normal distribution here. If they don't, since the mean calculates with all the numbers and is going to be most sensitive to outliers, if the mean is pulling over to the left side, you're going to have left skew. If the mean is pulling over to the right side, you're going to have right skew. The median was a resistant measure of center. Resistant meaning to the outliers. You could have a really big outlier in there and it's not going to make much of a difference other than the fact that it's adding one more data point to the whole set, or 2 or 3, however many outliers you add. But since this is the middle by location, that doesn't make much of a difference. Okay, and then the mode, remember that was the most frequently occurring data value. Okay, then when we talked about the measures of variation, what we were talking about is the spread. How far the data spreads, how far it distributes out. And the standard deviation was a critical value to calculate, to determine that. What it basically is it's the measure of how far on average all the other pieces spread from the mean. To demonstrate this, I'll go ahead and take the Academy Award winners for the Best Actress Award and add all their ages into this list here on Excel, where I can very quickly calculate out the mean, the arithmetic mean, and then the standard deviation. In fact, I'll point out here that the standard deviation, remember, comes in 2 classes, the population standard deviation and the sample standard deviation. And that's really important to start focusing on even more so now than ever when we're entering chapter 6 and so on, because because we're going to be talking about statistics and parameters and how the statistics estimate the parameters and which estimators are good, which estimators target the population parameters, and which don't. So anyway, I'm going to be treating this like a sample, so I'm going to use standard deviation of a sample. The calculation is just slightly different. In fact, I'll remind you what it is here. You can always just open up your approved formulas and review sheets because it's on there. It's in the fold out. And again, really you should have these things printed out and looking at them and just passing them, flipping through them regularly. So here is the calculation for the sample standard deviation, denoted by S. And pause for a second in your mind. Do you remember what the standard deviation notation was for the population standard deviation? Sigma. Yeah, lowercase sigma. And the difference in that is this would be a mu right here because it would be the population mean. And this would be capital N down here, not n minus 1. So either way, let me go back to this set. So now that we have the standard deviation, sorry, I guess I did not finish that. Now that we've got the standard deviation here, we can see what the middle of that data set is by mean, and what the distribution, how it moves over one standard deviation at a time. Now, the best way to probably see this is to put it on something like the dot plot. So let me try that. All right then, the mean was 35.7, and this is supposed to start, relatively speaking, at 0, go to 80. And 35 would be 31 to 33, 4, 35.7 would be about right here. So you imagine that someone posts a flag right here. I'll put a little X bar on it where the mean is. And then And then they say, okay, well, then how far is one standard deviation? How far on average do the other numbers deviate from there? Because clearly, the number 34, there was an age 34 in the list. They would deviate by 1.7. And then, the number 36, they would deviate, I'm sorry, this one right here was 35. So that one would deviate by 0.7, and 36 would deviate by 0.3. And so, those are very small. But then you've got one over here, like 80, that's going to deviate by, couple tens and, or what exactly is the number? It would deviate by 44.3. So that's a huge deviation, but average all those numbers, because those deviations are numbers themselves, average all those up, and this is what you're essentially getting. You're getting 11.1 distance. So you're going to imagine a spread of 11.1 from here. So let's just go ahead and imagine on this distribution really fast. 11.1 plus the mean is going to be 46.8. That means we're going to go from here, 11.1, and that would be 46.8, right around there. So that's one standard deviation to the right. And so when we get used to this language, when we say within one standard deviation, we mean right and left. That was probably a little bit short there. Sorry. Maybe out to there. And then you can imagine within two standard deviations. So, we've got full 11.1 and then 11.1 again. And when we say within two standard deviations, we mean both directions, right? And then we can go on, say within 3 and so on. So this isn't the best picture, but it doesn't really matter what distribution I'm looking at, the histogram version or this dot plot. It's just the idea that I'm going to be moving over the actual number of the standard deviation, so the 11.1 distance in value. And that's how standard deviation works. And that was really important for us. Okay? Then what did we learn? There were shortcuts to this process where you thought that in a usual set of data, the range would distance 4 standard deviations. So if you wanted to approximate the standard deviation, you could essentially just take the range and divide by 4, and that would be about 1 standard deviation. Remember, range is the max minus the min. So, so the usual minimum, in other words, is the mean take away 2 standard deviations, and the usual maximum would be the mean plus 2 standard deviations. So going back to that picture that I had, we'd expect that our usual min would be around here, and that's not true because I wasn't running the numbers exactly. In fact, if you take 35 and you take away 22, you're not at 0. So my bar is obviously a little bit off. In fact, what would it be? So we'd have 13.5 as the usual minimum and 57.9. Now, clearly this set wasn't usual and definitely wasn't normal, but we'd already talked about how, in fact, let me scroll up, how this had a right skew, and that it was that there were more younger females winning the Academy Award, Best Actress awards. And so we look at the within 2 standard deviations, we actually fall below our minimum. I don't know if you remember, but if you look back at the set, the youngest age person was 21, and we can actually calculate that by using, in Excel, since we already had the list, we can just do minimum of the list, and we get 21. So the 1 standard deviation would be right here, where we've added 11.1 to the mean and subtracted 11.1 from the mean. And then a 2 standard deviation would be right here, where we've added 2. Or, let me go past the scale that I had. We've actually contained all the data on the left side when we go this far. Oops. But that would be 2 standard deviations to the left. And that's the 13.5 and the 57.9, which is over here on this side. either way, so we start to think about how to imagine or consider the usual data. So let me go back to that as being plus and minus, and that would give us using the range rule of thumb, a range of 4 standard deviations, and pretty much contain all of your data. The empirical rule, actually, let me see if I can show us that and remind us. This follows along the same lines of thinking, that we, within 1 standard deviation, we contain 68% of our data. Within 2 standard deviations, we contain almost all of it, right? 95%. And then the 5% mark is where we benchmark our statistically significant, but there is still some data left out here. Another, 4.7%, and then a little bit more beyond that. But the empirical rule really focuses just on this 68, 95, 99.7. In fact, that's the other name for it, is the 68, 95, 99.7 rule. But it helps us to imagine how the normal distribution would look. And then there's some others, so I'll just go ahead and leave those out to come back to the relative standing, because this starts to give us a little bit more ready for what we're going to do in Chapter 6. So again, this was still all Chapter 3. So then in Chapter 3, we also defined what a standard score would be. And a standard score would be calculated by taking the deviation of any score that you're looking at, maybe age 21, that minimum score I was talking about, and subtracting that from its mean, subtracting the mean from that, and it's important that you follow that direction. You find the deviation where it's the data point minus the mean, and dividing by its own standard deviation, the standard deviation from its set. So in fact, let's look at that for that young age of 21. Switch back here. What would this one as a standardized score be, a z-score? Well, it would be 21 minus 35.7 divided by 11.1. Make the z look nicer. And we would get a negative 1, and we like to, for z-scores, these standard scores, we like to go to the hundredths. So a negative 1 and 32 hundredths. Let's see if I can get this. Now these standard scores are going to frame the standard distribution that we'll look at in the continuous distributions of Chapter 6, but I'm not quite there yet, so let me go back to what I was saying about the relative standing. In Chapter 3, we had also then said that then anything on a standard score, because remember, these standard scores are really just measuring the standard deviations, movements in the distribution. So this would be 1 standard deviation movement in the distribution to the left. This would be 2, and so on. Well, if the range rule of thumb says that, usually we're going to be able to fit 4 standard deviations in the range, then things beyond that usual range would be considered unusual. So standard z-scores that are like negative 3.2 would be considered an unusual value. So we talked about what was ordinary and unusual back in Chapter 3, and those things still exist here in Chapter 6. Then we defined the quartiles, and that was so that we could build up the 5-number summary, where we have the minimum as the first number, first quartile, which is the 25th percentile, as the second one, then the median, which is the location middle, and that is the 50th percentile, or in other words, the second quartile, then the third quartile, then the maximum. So that's our 5-number summary right there. And it allows us to build up another form of a distribution, a box plot. And here's just an example. And the box itself becomes another special range, an interquartile range, where we're in the middle quartiles right there between Q1 and Q3. And the whiskers that came out of it, which extend to the minimum and extend to the maximum, those start to help us to identify outliers, where an outlier would be something that was over 1.5 times this interquartile range. So you imagine this distance right here once, and then another half. And if anything falls beyond that, it's considered an outlier to the right. Similarly, once, that whole distance once, and then another half that distance. Anything falls beyond that to the left, it's going to be considered an outlier on the left side. So let me see if I had any examples of those. There's a quick reminder of a nice Bell distribution would have all of our data between our min and our max, and fitting in with the box in the middle proportionally, where you have the median right in the half of the box. Okay. Notice that the whisker is going to be a little bit longer, and on the uniform one, the distances are all going to be the exact same between each of the quartiles. Then you've got some skewing. This is like that actress award skew. I want to see the modified box plot here, though. Ah, there was one right there. So these are outliers. These are obviously extending beyond 1.5, 3 halves of a box. So you take one box, that's a whole one, take another half its distance. Anything beyond that is going to be considered an outlier, and this original data set must have had points that were on it, because these are indicated with the asterisks. Okay. Well, lots of outliers there, and that makes sense because we've got skew. When we have skew, we're going to have a bunch of outliers. Okay. Now I have little to say about chapter 4. It gave us some of the probability definitions that we needed, and we looked at how to do some counting, which is necessary for chapter 5's binomial probability distribution. But chapter 4 is mainly just branching us from the observed values that we were seeing in chapters 2 and 3, where we just observe some data, summarize it, picture it, visualize it with graphs, but it was still observed data, to the expected values that we're going to start to talk about in chapter 6, and we started talking about in chapter 5. So we use probability to bridge that gap. And here's a quick, let me enlarge this, a quick illustration to show that bridge. We went from the observed frequency distribution to determining how to figure out probabilities of events occurring, and sample space and all those related terms, and converge that into chapter 5, which is to create probability distributions. Now in chapter 5 we focused on the discrete type, where you remember that discrete means that they progress in countable number values, like 0, 1, 2, 3, numbers of girls, for example. And then the continuous kind we'll talk about in chapter 6, or we are talking about in chapter 6. So let me demonstrate. And by the way, that these terms, discrete and continuous, they came originally to us in chapter 1, and they're only returning to us now. But we have described these in chapter 1 when we were describing like the number of eggs that a hen lays, as opposed to the amount of, let me show you this one, the amount of milk that a cow can produce. So they're not going to produce exactly 2 gallons or 3 gallons. There's an arbitrary cutoff to that value, and that's the definition between the two, the difference between the definitions. You can go back to chapter 1, by the way, to remind yourself discrete versus continuous. Okay, so it's the same idea. In both cases, there's the basic requirements for the probability distribution, and that is that the data values are appearing by randomness. There's some element of chance for their occurrence, and their probabilities follow within, what probabilities should fall within between 0 and 1, the total of all of the probabilities adding up to be 1. Okay, so now here is an example of a binomial probability distribution where we have here the sample size, or the number of trials, being 8, and the probability of success, the constant rate of success, of being 64%. But we can change it around dynamically, so we could make the size bigger, and then we could make the rate of success bigger or smaller. And what we'll see over here is the actual probability distribution laid out in the table format. Just imagine that this first column is labeled x, and the second column is labeled p of x, as we normally do it. So x would be like, imagine we're having 16 kids. I don't know. Let's make it similar to the ones that we did in the homework. Let's imagine that we're having 5 kids. And out of 5 kids, we're trying to figure out how many are going to be boys, for example. There is the possibility that none of them are boys, or that only one of them are boys, or the 2 of them are boys, and so on. And over here are the probabilities that that could happen, that you could have exactly 2 of your 5 kids being boys. And apparently that's that would be, well, hold on just a moment. The rate of success to be a boy is not 9%. It's actually, let me get the portion out for you. The last number that I heard is that there are 100 boys for every 106 girls. So I'm sorry, how am I trying to calculate that? So I'm going to make that 100 divided by 206. If there's 100 boys for every 106 girls, and that means that the rate of having a boy is 48.5, and we'll just go to 48. So this would be that distribution, right? If the rate of success remained constant. And this is assuming we're not doing any sort of like special infertility treatment or things like that. So having exactly two boys, 32%. Anyway, now I actually don't like this probability histogram. I know that the book talked about probability histograms. They're all using the same following the same requirements that we have for probability distribution, and that is that the sum of all the probabilities is 1, and each specific height is a probability, so that means it has to range from 0 to 1. But I liked it a lot better in StatCrunch, where it has these drawn out as bars, just straight lines, because there is no, since we're looking at this in a discrete way, there is no gap, there's no space between here that's going to fill up. It's just going to be from 0 and then to 1, and the 0.5 is not being represented. The 0.75, the 0.25, nothing happens there, because in discrete probability distributions there isn't any possibility of having half a boy, or having like 1.3/4 of a boy. So either way, if you can remember, or if you use StatCrunch, you can check it out and see how they represent their discrete probability distributions. It looks nice. All right, so that's what we talked about in Chapter 5, and then we determined how to find out in general the mean, standard deviation, variance, and so on from the probability distribution. And then we got more specific when we talked about the binomial one. And the binomial one just had a couple other requirements. It was that there's a fixed number of trials. Each of the trials were independent. They were classified into 2 categories, and the probability of success remained constant. There are other discrete probability distributions, but those are the only ones we looked at. We didn't do the section on the, I'm not sure if I'm ever pronouncing it right, but Poisson. But in the binomial one that we did do, we used what we learned in Chapter 4 to calculate the number of ways that these things could occur, like having exactly 2 boys. How many ways can that occur when you're having 5 kids? And that was using this permutation calculation here. Combination. Permutation would not have this divisor here. So this combination, so you found out the number of combinations of ways that you could have 2 boys out of 5 kids. Then we multiplied that by the having 2 boys success rate times the probability of not having 2 boys, and so the remaining 3 boys not being a boy, remaining 3 kids not being a boy. And then that was Chapter 5. So, all right, now we're ready to talk about 6, but I'm realizing that at this point you're probably a little tired, and should either take a break if you haven't already, or I will force you to take a break. I'm going to end the video here, and I'm going to start another video to this whole big picture idea, and it will start right from here. So hopefully you'll have watched up to